So Bismillahir Rahmanir Rahim. Today we will talk about the momentum, collisions, we will discuss the rockets, and we will also discuss the projectile motion. So we start with the momentum. Momentum. So momentum is the quantity of motion in a body. So it's a vector quantity. So it has a magnitude and a direction. So it's the defined mathematically is the mass divided by the velocity. So it's mass. So the units in the SI unit is the kg for mass, and then we have the meters per second. So this is the unit of the momentum. So what we see here, so this is the quantity of the motion in a body. So if we have the higher mass, the momentum will be higher. If the body is moving with the velocity is high, so the momentum will be high. So they are directly proportional. So the momentum is directly proportional to the mass and the velocity. Now we discuss the relation between, since it's related to the motion of the body. So in the previous lectures we discussed the Newton's laws, and now we will try to find out that how the momentum is related to the Newton's laws. So now we discuss specifically the momentum. So momentum and Newton's second law of motion, second law. So for example, we will discuss an example in which a body, so we have a body, so this body has a velocity, so there is an object which is moving in this direction, and this is the initial velocity. Vi is the initial velocity, and after some time a force is applied on this object. So this object was moving in a straight line with the velocity, with the initial velocity Vi, and there was a force was applied for some time t. So after some time, when the force is applied, so the velocity is either reduced or it's increased depending upon the direction of the force. So after some time the velocity is changed, we have the Vf. So this is the system, and now we will see, we will solve this equation or this example mathematically. Since the force is applied, according to the Newton's second law of motion, there must be an acceleration, because according to the second law of motion, if there is a force applied, there will be acceleration in the direction of the force, and the magnitude will be equal to the mass multiplied by the acceleration. So first we want to know what is that acceleration. So acceleration here is the Vf, the final velocity, minus initial velocity and the time for which the force was applied on this system. And according to now the second law of motion, we have the F equals ma, or we can also write A equals F by m. So we have the acceleration is equal to force divided by mass, and here we have the acceleration equals to final velocity minus initial velocity divided by the time for which the force was applied on this object. Since they are equal, so this term and this term are equal to the acceleration, so we can write here Vf minus Vi divided by T is equal to force divided by mass. And now we want to know what is the force. So force, if we move this the mass here on this side, so we will have the force. So the force is mVf minus mVi divided by time. So what we see here, this is mv. mv means mass multiplied by the velocity. If you look at the definition of the momentum, so we have the mass multiplied by the velocity. So this term here, is the momentum. Since this is the final velocity, we can say that this is the final momentum of this system. And this is mvi, so momentum of the system, which is initial momentum. So we can write Pf momentum, which is the vector, and we have the Vi divided by time. So what we see here, that the force, which is a vector, is equal to the final momentum minus initial momentum divided by time. So it means that if the denominator is the change in momentum. So the final momentum minus initial momentum, so the change in momentum. So what does this mean? It means that if the momentum of a system is changed, it means that the force is applied on a system. So if the force is applied, in other words, if the force is applied on any object, the momentum must change. Momentum of the system must change. The force here is the rate of change of momentum. So for this we can also write that the delta P divided by delta T. And now we want to discuss an example which is related to this relation here, the force which is related to the momentum here. So we have an example in which a car which has a mass of 1500 kilograms is moving with a velocity 20 meters per second, and there is a force that is applied on this system or this car, and the velocity is reduced to 15 meters per second, and we want to know what is the force that is applied. So we have a car. So we have the Vi here is the 20 meters per second, and after some time when it was moving with 20 meters per second, there was a force that is applied on this object. So we do not know whether the force is in this direction or this direction, but there is a force that is applied. So this force we want to know, and when the force is applied, the velocity, the final velocity after the force is applied is 15 meters per second, and the force was applied for 3 seconds. So 3 seconds. So this is the time. So what we see here, that initially the velocity is 20 meters per second, and after the force is applied, it reduces to 15 meters per second. So we can predict that the force that is applied must be opposite to the velocity, because it is reducing the velocity. It is reducing the velocity of the system. So we will use this relation here. So we use this relation. So we want to know the force. So we have the mass. The mass here is 1500 kilograms. So we have the mass here, we have mass, we have the final velocity is 15, and we have the initial velocity which is 20, and for the time we have 3. So if we put these values, if we calculate it, we will get that the force is minus 2500 newtons. So what we see here, we have a magnitude, but with the magnitude we will get the minus sign, and the minus sign is telling us that the force is in the opposite direction of the velocity. That's why the velocity is reduced to 15 meters per second from 20 meters per second. And now we discuss the conservation of momentum. The conservation of momentum means that there will be no change in momentum if there is no external force applied on the force. on the system. So what we see here, if the force is applied, the momentum will change. But if there is no external force on a system, this momentum will never change. So the change in momentum means the final momentum and the initial momentum will be the same. So if they are the same, means this term is 0, so the force is 0 here. So the conservation of momentum, according to the law of conservation of momentum, if there is no external force that is applied on a system, there will be no change in momentum, or which means the final momentum will be equal to the initial momentum. And right now we will discuss this conservation of momentum. So we have the conservation of momentum. So we have a system of particles. So we have so many particles. So we have particles. So these particles, we can consider this particle as a gas particle, for example, or on the big scale, we can also consider this particle as a stars. For example, there are hundreds of stars. So we have an unlimited number of the stars, and there is an external force on this system. So for example, we take only two particles. So one particle is here, and there is an external force. So this force, this particle is feeling an external force. So this is the external force, and we call this particle I, and we take this another particle which is J. So this force is the Fi, external force. So this external force, and this particle is feeling an external force which is Fj external. But since this is a system of a particle, there must always be internal interactions, and this internal interaction can be electrical interaction, they can be springs, or they can be a gravitational interaction. But we do not care which type of interaction it is, but we just consider these forces as the internal, we call this internal interactions. So for example, between these two particles, there will, for example, we just consider the gravitational force. So the gravitational force, there will be a force in this direction, and we call it Fij. So this is the force that the Fi means this particle, the I particle, is feeling because of J. So the gravitational force, they are attracting each other. So on the other hand, this particle will also feel the gravitational force, and we call this particle, this force is Fji. Fji means that the J particle is feeling this force because of the presence of the I particle or the object. Since they are feeling the same force, according to the Newton's third law, these interaction, the internal interaction, will cancel each other, and now we will use the addition of the vectors. So how many forces are acting on this particle? We just ignore all other particles, and then we will discuss these particles in a general way. So we consider, or we concentrate only on this particle and this particle. So how many forces are acting on this particle? So we have the one external force and one is the internal force. So we use the head to tail rule or parallelogram method. So this is the net force that this particle is feeling. So this is the force, net force. And similarly, if we use the parallelogram method, this particle is feeling the external force. So this is the Fj net force, and this is Fi net force. And now, according to the Newton's third law, this Fij is equal to minus Fji. So this force and this force, they are cancelling each other because they have the same magnitude but opposite direction. The only force that we can consider or that's really affecting the system, these are the external forces. So the total momentum of this system, we can write, so the net momentum, so the total momentum is total P total is equal to particle 1 means the momentum of the particle 1 plus momentum of particle 2, and then we go on and then we have the particle I. So infinite number of the particle. Time rate of this momentum, so this is also a vector. So we will have a force that we just discussed according to the Newton's second law, that when we discuss about the relation between the Newton's second law and the momentum, we found out this relation. So the time rate of change of momentum is force. So we take this is total divided by time. So this is the force then. So this is the force on one particle. So this is the net force on one particle. So this is this net force here. Plus 2 plus F3. So then we go on. So we have the Fi. And then it's infinite number of particles, the forces, and we have on the infinite number of particles. But the net force is only the external force, because all the internal interaction, they are cancelling each other. Whether it's the gravitational interaction, it's the electrical interaction, or it's any other kind of force, internally that cancel each other. So when they cancel each other, the only force that will be left, so this is also a total force, the momentum divided by time is force. So this is the total force is equal to the F total external force. So this is the external force. So what we see here, if there is an external force, then the momentum of the system will change. But if there is no external force, all the internal interaction or the forces will cancel each other and the momentum will not change. The only thing that can change the momentum of a system is the external force. If there is no external force, means there is no change in momentum. So what we see here, that the momentum of the individual particles because of the internal interaction may change, but we are talking about the momentum of the system itself. So the individual particles, because for example when they collide with each other, or more than one particle or more than two particles interact with each other, so the momentum of the individual particles will be changed. But the total momentum, if we sum up the momentum, if there is no external force, so this is the external force, so this one, if there is no this force here, the only force that we will have are these two forces, and according to the Newton's third law, they will just cancel each other and there will be no change in momentum. So the only force that can change the momentum of a system is the external force. So in other words, if there is no external force on a system, there will be no change in momentum. Now we take the example of two particles. We just take two particles and we try to understand the conservation of momentum of those particles, and there is no external force, as we just discussed. If there is an external force on a system, there will be a change in momentum and the momentum will not be conserved. We ignore, so the internal interaction, they will always cancel each other. So the only force that can change the momentum of the system is the external force. Now, so we take the isolated system. So isolated system means that it's isolated from the outside environment. So we take the isolated system, it means that the external force, so the F external is 0. And so we have the two particle system. So we have the particle 1, which has a mass m1 and it's moving with the velocity v1. And we have another particle, we have the m2 and it has the velocity m2, now v2 here. And after, so this is the before the collision, so they are moving towards each other, and after some time they will collide with each other. So after some time they will collide with each other. So this is the collision here, and after collision, so we will have the m1 here, so the masses will remain the same. So we have the m2, but they will move in opposite direction, or depends on the, we will just discuss the collision itself soon. It depends in which direction and will they move. It all depends on the masses and the velocities, initial velocities on of the system. So after collision, its velocity is, so we put a dash on the velocity, and the dash means here that this is the velocity after the collision. So we have the similarly v1 and we put a dash here. And now we just write the momentum of the system before the collision and after the collision here. So the momentum of the system before the collision, so they will feel each other, so they will feel a force when they collide with each other, but this will be internal force that we just discussed in our previous example. So right now, because of the change of because they collide with each other, so there will be a change of the momentum because of the collision, and we write that change of momentum. So we just discussed that the force is equal to 1,2. So F12 means that the force that the M1 felt because of the M2 here, multiplied by time, is equal to, after momentum, so after collision, we have the F1 minus P1. So this is the momentum of a particle. So this is the momentum of this particle 1 here. And now we want to write the similarly F21 multiplied by T equals M2. So this is the final velocity, final momentum here, and we will have the M2V2. So this is the force, this force because of the collision force. So these forces are the internal forces. There is no external force. As we just said, these two are the internal forces. So if we add these two equations here, so what we will get is the F12 plus F21, and the time here is the constant. So we will get that the M1V1 minus M1V1. So this part plus M2V2 minus M2V2. Since these are the internal forces, so they will cancel each other according to the Newton's third law. So they will be the same forces, and they will in opposite direction, so they will cancel each other. So this force, this term will be 0. So if this term is 0, then we can write F1 V1 plus M. So we just rearrange this term here. So we will have the V2 equals M1 V1. So this is the M2 V2. So now we try to understand it. So what we see here, so this is the initial velocity. So this is the initial velocity, and this is the initial velocity of the particle 1, and this is the initial velocity of the particle 2. So if these are the initial velocity, means that this is the initial momentum of particle 1, and this is the initial momentum of particle 2. Similarly, this is after collision, this is the final momentum, and this is the final momentum of the particle 1 and 2. So what we see here, that the initial total momentum before the collision is equal to the momentum that is after the collision. So this is the conservation of momentum we just discussed generally for the many particles. And now for the two particle system, we said that there is no external force. So if there is no external force, the total momentum is conserved, which means that the momentum before the collision and momentum after the collision will remain the same. So there is no difference. So they are equal.